Hi there, I am here to introduce the sampling process of group 3 noise. Sampling is a process to convert continuous signal to discrete signal. We can use the audio info and audio read function to get information of the audio file and read the audio file. The continuous audio signal can be plotted using plot function. The sampling frequency is set 2 times of the maximum frequency of audio file. The length of the signal and the number of samples are determined, and we can plot the discrete signal using stem function. The output waveform of the discrete and continuous signal is shown as below.
Hi, my name is Lina Tri. So today I will explain how to use the convolutions to filter the noise. Convolutions is using two inputs to filter one through the other, and the convolutions of one function, which is input signal, with second function, which is impulse response signal, will give the output of a linear time invariant system. So from the mallet code, the convolution code is y equal to COMV bracket S and H. Before that, we need to generate the input signal and also the impulse response signal. To undergo the convolutions to form an LTI system by using a stem functions to determine the length of the value along. So this is the output after convolutions process. Next, state transform is used to plot region of convergence and analyze the stability of the system. First, the magnitude and phase of the imaginary zero will be defined to generate conjugate pair for the imaginary zero. Next, real zero will be defined and all the zero will be listed in an array. Same for defining the imaginary poles as well. After that, by using z-plane mallet functions, poles and zero will be plotted. So beside the mallet code is the result by using z-transform mallet code.
For the IR filter design using bilinear transformation technique, we use DTFT to determine the spectral response of the audio signal using the absolute and FFT function. The audio signal in frequency response is plotted. The parameters of the Butterworth filter are defined. The bilinear, Butter, and Butter functions are used to design the Butterworth filter to filter the audio signal in frequency domain. The filter process is carried out using filter function, and the audio that has been filtered will be write using audio write function. The filter audio file in frequency domain is plotted.
Hi everyone, my name is Lee Jia-Heng and I will be presenting for the DTFT and windowing method. First, discrete time Fourier transform DTFT is to convert the time discrete signal into frequency domain representation for the analysis of the system frequency response and to get the magnitude, pattern, and phase pattern of Hz from Hn. And this is the mallet code for the DTFT process. We can see that first we convert the signal to frequency domain. After that, we obtain and plot the magnitude and phase response of the input signal. So next, we have windowing method that multiplying the ideal impulse response with window function to generate a corresponding filter which stable the ideal impulse response. So from the mallet code, we can see that first we define the frequency response of the input signal, and we need to determine which type of windowing function that will be used. And finally, we do the multiplication of these two functions. It is also quite similar to convolution method, just that the windowing method is the transcription process of an ideal filter function and a window function in time domain.
Hi, my name is Kek Seng Yang and I will be presenting the first part of our mallet code. At first, we need to use this audio read function to load the audio file into our mallet workspace. And now let you hear how does the voice sounds like.
79709.
And then we will plot it in time domain by using stem functions. As you can see, this is the result. And now we will convert it into frequency domain by using FFT, FBS, and angle functions. And then we'll extract the length of the data, shift it to left by 1, and then convert it into angular frequency by using these equations. And then we'll plot the responses by using omega per pi as the x-axis and y mag and y phase per pi as the y-axis respectively. And now let's do the how is the results. As you can see, the noises are mainly located between 0 pi until 0.2 pi radians, which means that we need to design a high-pass filter in this case.
For the mallet code, we use audio read to read the wave file with the sampling frequency. And then for the designing of filter, we design a bilinear high-pass filter with the specification listed here. We are using Butter and Butter to find the Ni and omega c, with also the Ba to create a transfer function. And then we are using the bilinear function to take the numerator and also the denominator. And then now for the Z transform, we can plot the ROC of the filter using dual poles and Z-plane. Then the last one, we filter the input signal to become the output by naming it Y filter. And then now we run. So this is the result we get. For the discrete time domain, we can see that the input and the output signal with figure 1 and figure 4 respectively. And then we can also compare figure 2 and figure 5 with the input and output magnetic response and phase response using DTFT. And then last one for the figure 3, we can use Z-sensor to see the stability from the zero plot. The last one is the audio write file, which is the output the audio file. So this is all the presentation from HomeGroupC. Thank you.